Good morning. My name is Nikhilesh, and this is my research project titled Enhancing Blockchain Security Using Multilayer Encryption for Improved Data Protection. This work focuses on addressing vulnerabilities in blockchain IoT integrations by introducing a defense in-depth encryption model that not only strengthens current security but also prepares for emerging threats such as quantum computing. Uh, In blockchain is known for decentralization and tamper resistance, but when integrated with IoT system, data in transit is still vulnerable, particularly when single layer encryption is used. And in this research, I propose a multi-layer encryption model combining asymmetric encryption for secure key exchanges, symmetric encryption for high speed data protection, and post quantum encryption for future proofing. The framework was implemented in Python, deployed with Ethereum smart contracts, and tested in a simulated IoT blockchain environment. The evaluation measured both performance metrics and resistance to common attacks like brute force and man in the middle. The findings show that this approach significantly enhanced security while maintaining low latency, making it particularly for real-time IoT applications. In the introduction, we have seen that blockchain adoption in IoT is growing in fields like healthcare, supply chains, and energy trading. However, most current implementation rely on a single encryption layer, meaning that if that layer is breached, the whole system is compromised. The need for post-quantum readiness further complicates security planning. My research question is how can multi-layer encryption enhance blockchain security and improve data protection in IoT ecosystems? The motivation is to build a model that not only secures today's systems but can adapt tomorrow's threats. In the objectives, the research was guided by four main objectives like assess existing blockchain IoT encryption practice and identify gaps, then design a multi-layer encryption framework integrating RSA, AES, and a post-quantum layer. Implement the framework in Python connecting to Ethereum smart contracts. Then the fourth one is evaluate its performance and resilience against attack simulations. The main aim was to move beyond theoretical proposals by creating a working, tested prototype. In the literature review, we can see that the literature revealed strong interest in multi-layer blockchain architecture, but also significant gaps. Studies by Pajo, Alomda, and NA and Park all explore layering and hybrid security, yet most lack empirical validation. Post-quantum cryptography was highlighted by Gargavi as an urgent need, but very few works actually integrate it into blockchain IoT systems. This gap inspired my framework, which combines classical and quantum resilient encryption in a modular way. In the research methodology, this was a practice lead experimental study conducted in four stages. The first one is a literature synthesis identified the design requirements, and the second one is I designed the multi-layered encryption architecture. The third, I implemented it in the Python using an IoT simulator for generating synthetic sensor data and canage for a local Ethereum blockchain. Finally, I evaluated the system's performance and security using defined metrics. This approach ensured that the solution was both theoretically grounded and practically validated. And in the encryption framework, the framework operates in three layers. The layer 1 is RSA 2048 for secure key exchange, and the second layer is AES for data encryption and bulk data encryption. And the third layer is a post-quantum element implemented where SHA 3512 for integrity verification, which modular compatibility for hyperstyle algorithm. The layer are applied sequentially, ensuring that compromising one does not expose the entire system. And in the blockchain integration, the encryption stack is integrated into blockchain workflow where encrypted IoT payloads are stored immutably on an Ethereum smart contract. The smart contract was written in Solidity, compiled and deployed using Truffle, and transactions were submitted from Python using web3.py. This approach replicates a decentralized edge to cloud model, ensuring traceability, immutability, and confidentiality. In the evaluation metrics, the system was evaluated along two main dimensions. Performance is measuring latency, encryption or decryption time, and throughput. In security, we have testing resilience to brute force and man in the middle attacks. And Matplotlib was used for visualizing results, ensuring both quantitative and qualitative measurements. And when we go through the result overview, the total encryption time across all three layers averaged just under 13 milliseconds, with AES taken 9.8 ms, RSA taken 12.1 ms, and SHA3 taken 7.3 ms. And the system successfully resists all brute force and MITM attempts during simulations. And the blockchain currently stored and retrieved encrypted payloads without corruptions. This confirmed that multilayer encryption is feasible even for resource constrained IoT environments. In the comparative analysis, when compared to single layered AES encryption, the multi-layered system added roughly 20 ms of latency but significantly improved resilience with stronger brute force resistance, complete MITM protections, and quantum readiness. In other words, the trade-off in speed is small, but the security gain is substantial, making it a compelling option for real-time IoT systems where data integrity is critical. And when come to the limitations, the study used simulated IoT data and a local blockchain network. So real-world edge cases may differ. And there was no energy consumption analysis, which could be important for battery operation operated to IoT devices. Some minor operational issues arose, such as file permissions errors when saving metrics and occasionally Solidity compiler mismatches, but these were resolved during testing. In the discussion, the strength of this work lie in its modular architecture, post-quantum readiness, and use of open source tools within a constrained hardware environment. However, further testing in live environments and broader attack simulations would be essential before large-scale deployment. In the conclusion, this research achieved all objective, delivering a tested multi-layer encryption framework that enhanced blockchain IoT security. It shows that security can be strengthened without sacrificing real-time performance and that post-quantum readiness can be embedded into today's design. And this research builds on contributions from authors such as Biswas, Pacho, Leravi, Valdez, Alomda, Sami, whose work informed both the conceptual design and the experimental evaluations. Uh, this is my PPT report. Thank you.